So it's a great pleasure to have Francesco Morabito from Paris with us today, who will be telling us about Hofer norms on braid groups and quantitative Heegaard-Floer homology. Take it away, Francesco.
Thank you very much. It's a great pleasure for me to be here today, and I would like to thank the organizers for inviting me, and I hope everyone has been having a good holidays so far. So today I'm going to talk about my work about Hofer norms on braid groups and quantitative Heegaard-Floer homology. So here is the setup. We consider underline L. So these are a collection of k disjoint, non-nested embedded circles in D. Up to renormalization, we may assume the area of the disk to be equal to 1, and the picture is the one on the left. So essentially, you want these circles to satisfy the following property. If you consider the complement of the circles in the disk, you have this connected surface of k plus 1 connected components. K of them should be disks, and the last one should be a pair of pants with k legs. Now, with this in mind, we can define a certain subgroup of the group of compactly supported Hamiltonian diffeomorphisms of the disk, which we denote by HAML of D. So it is made up of those diffeomorphisms that preserve the collection of circles as a whole. So for the following throughout the talk, if I say Lagrangian link, Lagrangian configuration, or something like that, I always mean this collection of disjoint circles. So a note is that the elements of this subgroup do not need to send a circle to itself. It may permute them, and even less is it required to induce the identity on any circle. In fact, so I have a picture right here. So this could be a good example. If you see L1 is mapped straight to the third element of the Lagrangian configuration. Now, given this subgroup, we can define a braid type function. So it is a function that associates the diffeomorphism its braid type. It is a morphism of groups going from the subgroup of Ham to the braid group on k strands. So a braid here is a collection of unordered k unordered paths from 0, 1 to the Cartesian product of the disk, which never intersect. So as soon as I is different from j, for every t in 0, 1, gamma I at t is different from gamma j at t. I would like to point out that this morphism is surjective. As soon as the circles bound disk, or I mean the typo here, they bound disks of the same area. For the definition of this function, the same picture still works. So the idea is is a simple idea, in fact. So we take any Hamiltonian isotopy between the identity and phi, the Hamiltonian diffeomorphisms in question, and we follow the circles as they move through the Hamiltonian isotopy. So this gives essentially a braid, so this collection of paths with thickened strands. So the braid associated to the main picture of the slide is the one here to the right. And you see that there are 2 points in the braid diagram where one strand passes over another, and I have written a plus and a minus. So when 2 strands pass one over another in the braid diagram, we have a crossing, and crossings may be either positive or negative. So a positive crossing is reading the braid from bottom to top. A positive crossing is given when by the left strand passing over the right strand, and conversely, if the right strand is the one passing over the other one, we have a negative crossing. So LK down here is the linking number, and I have been talking about crossings essentially because the linking number is given by the sum on all the crossings of the signs. So this braid over here, for instance, has linking 0. This I'm giving on the right is its description using the usual presentation of the braid group, but we will not really need that. So reasons why I have given this picture. The first one is, as I mentioned, to fix the ideas, it's useful to see a braid in which a circle is mapped to another circle, so that you know that the Lagrangian configuration is only preserved as a whole. But especially, so this is a braid with 3 strands, which is non-trivial. I mean, of course, because the first circle is mapped to the third one, whereas, so the trivial braid is given by 3 parallel lines. It cannot satisfy the same property, but which has linking 0. So in principle, when you have more than 3 strands, the linking number does not determine the braid you have. You can have arbitrarily non-trivial braids with 0 linking. However, if k is equal to 2, 2 braid diagrams represent the same braid if and only if they have the same linking number, so the same sum of crossings with signs. So this is the question we would like to tackle. We are looking for a way to bound from below the Hofer energy we need to realize a given braid in the class of Hamiltonian diffeomorphisms that fix a given Lagrangian configuration. There is an equivalent definition for this question given by, given in the language coming from an idea of Frédéric Leroux. So we would like to define pseudonorms on BK. So they are actually norms of groups, so that the norm of the inverse coincides with the norm of the element and it satisfies triangular inequality. So to any braid, we associate the infimum of the Hofer energies of diffeomorphisms having that braid as braid type. We would like to find a function from BK to R, therefore, which is Lipschitz with respect to this norm and hopefully non-trivial. And that is precisely the content of our main result. So we do need to assume here that each of the K circles bounds a disk of the same area, A. A is a real number between 1 over K plus 1 and 1 over K. And then we have a uniform bound on the Hofer energy of a diffeomorphism given by a constant, which only depends on the Lagrangian link, in particular on the number of circles you have and the area which is bounded by each one of them, times the linking number of the braid associated to the diffeomorphism in question. This translates to an inequality in the norm, in the norm associated to the Lagrangian configuration we are looking at. Is the statement clear? If you have any question, please do feel free to interrupt me. If not, I will give some remarks. So the first one is that the constant is in fact explicit, and by the end of the talk, I will point out where the constant comes from. But in general, what you do need to know is that the constant goes to 0 when k goes to plus infinity. So essentially, the estimates get worse and worse as we consider more and more circles. And also when a tends to 1 over k plus 1, which is the lower bound of the admissible interval of values for a, the constant goes to 0. This is not a limit of the model. In fact, there are counterexamples. So if disks become too small, we can form arbitrarily complicated things with bounded Hofer energy. At least there's a counterexample again by Frédéric Leroux. Now, we would like to also point out that this gives a new persistent phenomenon. So if we consider two Hamiltonian diffeomorphism phi and psi, we can bound from below the Hofer distance by the same constant times the absolute value of the difference between the linking numbers of the two braids associated to each one. Now, the thing is, as I mentioned, the linking number does not tell you everything about the braid. In general, it's very far from that. That is very far from being true. But if you have two braids, we know everything. If k is greater than or equal to 3, we can have different braids with the same linking number. And in particular, we cannot prove by with these tools non-degeneracy for norms associated to, on such braid groups associated to Lagrangian links of at least 3 components. Non-degeneracy was proved by Chen last year in September. So he proved that if two diffeomorphisms in Hamel of D define different braids, then the Hofer distance is bounded from below by a constant which only depends on the Lagrangian link. However, that is a very rough estimate in general. The last consequence I would like to bring to your attention is the fact that using these estimates, we can provide a simple class of Hamiltonian diffeomorphisms which have zero Calabi and arbitrary asymptotic Hofer norm. So the reason is actually very, very simple. We can realize the trivial braid with a diffeomorphism of arbitrary Calabi. You can just take a Hamiltonian whose support is contained in a disk. It can have arbitrary Calabi, but it will also induce a diffeomorphism with associated trivial braid. And since the right-hand side of this estimate is in fact homogeneous under iterations of phi, we find what you want. We can always bound from below the asymptotic Hofer norm of any diffeomorphism with this property. So the rest of the talk is devoted to, first, some early results of this kind, and then I'm going to talk about the tools we need to prove the whole thing. So if you have some questions, I would be happy to answer. Otherwise, I will just carry on. Okay. So early results, at least to the best of my knowledge, that's two of them. One of them was proved by Frédéric Leroux in 2010, and the other one by Michael Kanevsky in 2011. So in 2010, Frédéric Leroux considered an annulus inside another annulus, and the subgroup of Hamiltonian diffeomorphisms which fixed the annulus as a whole. And to that subgroup, to every element in that subgroup, associated a rotation number. So which is, very intuitively, and also very clearly, it's just the number of times a point would wind about the center of the annulus, and proved the same kind of estimate essentially. So the Hofer energy of such diffeomorphism would be bounded from below by a constant times the absolute value of the rotation number. And Kanevsky did something similar, but instead of having an annulus inside the annulus, he considered a disk inside the annulus which was non-displaceable. Also, in that case, we have a rotation number and the same kind of estimate on the Hofer energy. I will just explain quickly how my result is a generalization of Kanevsky's in a certain direction. So one can see a Hamiltonian diffeomorphism of the annulus as a Hamiltonian diffeomorphism of the disk, which fixes the discrete side throughout any isotopy going to that diffeomorphism. So essentially, the idea is that seeing this disk inside contained in the annulus as a second disk, in my theorem, we can let both of them move around the Hamiltonian isotopy. However, Kanevsky's result is stronger in another direction, which is he's not asking for any area condition on the inner disk, whereas I have to assume that the inner disk and the disk D, which is filled with red in the picture, have the same area. Okay, now the tools we use, as announced in the title of the talk, come from Quantitative Heegaard-Floer Homology, and in particular, they are the associated spectral invariants and quasimorphisms. So Quantitative Heegaard-Floer Homology is a Lagrangian Floer theory on on Lagrangians in symmetric products. So the construction and the context is the following. We take a symplectic surface sigma, and we consider its kth Cartesian product. Sk here is the group of permutations of k letters, and it acts on the Cartesian product by permutation of coordinates. So we may consider the quotient. The quotient is in general not a manifold, but it's not naturally a manifold, but in this specific case can be given a smooth structure. And in fact, by some work of Timothy Perutz, it can be given a Ecole structure, so it is symplectic. In particular, so Timper-Roots defines a symplectic structure in the quotient, which coincides with the push forward of the product symplectic structure outside a very small neighborhood of the diagonal. The diagonal, so it will be noted by delta in the following, being the what would be the singular locus of the quotient. Then we can consider a collection of K circles in sigma. They have to be disjoint and embedded. This collection passes to the quotient into a Lagrangian torus. So it is Lagrangian, in fact, because the form given by Perutz coincides with the push forward of the product symplectic structure outside of the diagonal, and these circles do not intersect. Moreover, if we assume certain area conditions, which we are not going to detail right now, the quotient Lagrangian is in fact monotone. So we can hope to do some further theory on that. And last ingredient, if we take a Hamiltonian diffeomorphism of sigma, if sigma has boundary, we have to assume that it has compact support. If phi is generated by a certain Hamiltonian H, we can define sim k of phi, a Hamiltonian diffeomorphism on the quotient, generated by the symmetric product of the Hamiltonians. So we're just going to sum Hamiltonians at every point of the tuple. So the Heegaard-Floer complex associated to the pair underline L and H is defined to be the Floer complex associated to the symmetric product of L with the symmetric product of H. So this gives rise to a well-defined Floer homology theory. So in particular, since the homology theory is non-zero, it yields Hofer-Lipschitz spectrum invariance, which we denote by CL of phi. In fact, the whole proof of the result hinges on a low-dimensional topological interpretation of a difference between spectral invariants. So to sort of explain that, I have to I have to tell you what generators of the Floer complex are. And I mean, they have to be capped intersection points, but what is a capping? So when defining the complex, we have to take a reference path between sim k phi of sim L to sim k of L. And in fact, in the setting we are in, where the two Lagrangians coincide, this is so it is a tuple of k paths, which represents by definition, in fact, b phi minus 1. So a capping, therefore, will be a homotopy between a trivial braid, which is given by a set of k constant paths, to b phi minus 1, which is the reference path. Why is that important? Because spectral invariants satisfy a spectrality axiom. In particular, they are, so their value, it's a real value, is the action of a specific generator of the Floer complex. So the action is given by this formula. So there are three terms. That's a constant. This constant, in fact, is a rescaling constant. So it only depends on the reference path we have chosen for the Floer complex. That's the integral of a symplectic form. The symplectic form is the quotient, the symplectic form to the quotient. And then there is a third element, which is what we really care about. So eta here is a monotonicity parameter associated, therefore, to underline L. And this multiplies an intersection product between the capping and the diagonal. So it is this third element that lets us extract the low-dimensional topological information. So we want to first relate this intersection product to the linking number and then extract it from spectral invariants. I will actually only do the latter because I have about 1 minute left, and I think it's more important. The idea is actually not difficult. So we have to embed the disk into spheres of different areas. So Si is a number between 0 and Ka minus 1, but that's not very important for now. So from the Lagrangian link we're given inside the disk, we find two different Lagrangian configurations into the two spheres. What is important is that eta 1 will be different from eta 2, so that when we look at differences of this kind, essentially the third terms will not annihilate each other. And similarly, so from a Hamilton diffeomorphism, we can obviously, on the disk, we can obviously find one on the sphere. And we are interested, therefore, on this difference. I do have 5 seconds, so I will just say that we have to identify the two complexes via an isomorphism. This identification does not respect the action, and the failure to respect the action is exactly given by the difference we want on one side and by the difference between spectral invariants on the other side. To compute that, we have to change couplings properly, and we can do that because of certain monotonicity properties of the Lagrangian link. So I am done. So thank you and Happy New Year.
Thank you. Well, let's thank Francesco again, however way you can. And perhaps we can have maybe one quick question from Francesco. I mean, remember, at the end of the session, we will have a longer discussion session. But if anyone has a quick question. Sure.
Yes. So could you tell maybe how you relate the spectral invariance to the Lincoln number and the constant that appears in the result?
Sorry, I struggle understanding what you're saying. If I understood correctly, you're asking me how to go from the difference between spectral invariance and the link to the Lincoln number, right?
Yes. Thank you.
Okay. So as I mentioned, we can change couplings so that the difference between the two spectral invariants is only given by this quantity. And by the way, this is going to be the constant CKA. So essentially, when we get to this difference after recoupling, we are assuming that all the couplings are entirely contained in sim k of t. So this is a subset of sim k of S2 for whichever area you want. And at that point, we can essentially choose any homotopy to realize the coupling by homotopy invariance of this guy. So to relate the intersection product with the linking number, essentially the proof I have goes by induction of the number of strands, but essentially, so if you have a braid with a certain number of strands, say you have strands, so it will do whatever you want on the first ones. And then you have the last one. So the last one will have to, will in general do weird things with the first k plus one, with the first k minus one. So what you can do is choose a homotopy which pushes the last strands, on the back of all the others. So it essentially makes it so that the braid you find after this is something like G in BK minus 1 union a trivial strand, and you can count intersections like that. So essentially you have to be careful about the signs, but every intersection gives you a difference of -2 in the linking number by definition, but it counts as 1 in the for this quantity. So that's how you relate this to the linking number. Is that clear?
Okay, very good. So perhaps we will continue on this a little bit more at the end, as I said. But for now, let's text Francesco again, and we'll have Philip joining.